Well, hello, pre-calculus students and seekers of general truths. Let us continue with our applications of derivatives. And again, like I mentioned before, this is barely scratching the surface of applications of derivatives, as there are entire courses and fields of study that uses derivatives. So we've seen examples of graphing already, and let's look at an example of what's called local linear approximation. All right, so we're going to start out by finding the line that's tangent to the graph. And to do that, we find the slope. But to find the slope, we need to find the derivative. So the derivative of this function is, remember, we're going to take the 2 and multiply it to the coefficient in the front. So this becomes negative 10x. And this coefficient here is just 1, so that's plus 1. Then we're going to substitute in 2. So f prime of 2 is negative 10 times 2 plus 1, which is negative 19. Okay, so this is our slope. But to get the equation of a tangent line, we need to find the point as well. And I'll just write it on the side here. So the point that we're using here is the only point that this tangent line passes through that we know for sure is the point on the graph as well. So that comes from plugging in 2, right, because this is at x equals 2 into f. So f of 2 is negative 5 times 2 squared plus 2 plus 3, which is negative 20 plus 5, or negative 15. Okay, so we know that the graph, or the tangent line, has a slope of negative 19 and passes through 2, negative 15. So the tangent line equation is y equals negative 19, and using what we know about point slope form, it's x minus 2, because we're shifting the original line 2 units to the right, minus 15. Okay, so that is the tangent line equation for the function f of x at x equals 2. Okay. Next, use the tangent line to estimate the value of 2.01 and then compare it to the actual value of 2.01. So let's estimate by plugging in 2.01 into the tangent line equation. So we get negative 19 times 2.01 minus 2 minus 15, which gives us, and just working out all of the arithmetic here, this is 1/100th times negative 19, so that's going to be negative 1, let me clean that up. This is going to be negative 0.19. All right, so it is negative 0.19 minus 15, or negative 15.19. Okay, so that's our estimation. Now let's look at the actual value. So the actual value is, if we were to plug in 2.01 into the original equation. Okay, so plugging it into the equation, negative 5 times 2.01 squared plus 2.01 plus 3 gives us a value of negative 15.1905. Okay, so this is the actual value, and this is the estimate. And you can see that the estimation is within 0.0005 of the actual answer. Okay. And so let's just see why that is. All right, so I'm going to pull up a graph of these equations and just show you why that is the case. All right, so I've got a graph of Desmos up here, using Desmos here. And the red graph is my original equation, and the blue graph is the tangent line. And you can see here that if I get closer and closer to when x equals 2, so x equals 2 is over here, so I'm going to go all the way down here. When x is equal to 2, So where's my line? Yeah. If x equals 2, you see that the blue line and the red curve are almost the same thing, okay? Now, if I zoom out, so right here at 2, -15, you see that all of the points, it's almost indistinguishable, so close that decimals can't even tell it apart from each other. Okay, so near the point 2, the tangent line and the actual function are very, very close to each other. Okay? And in fact, we can see that in our example, they are within 5/10,000th of the answer to each other. And so this is where the name local linear approximation comes from. Local means that it's close. Linear, we're using a line. And approximation, well, we're using an estimation. Okay? And so this is the idea of using a tangent line to approximate values of the actual function. Okay? So local, again, means that it's near or it's close by. Linear, here we're using a line, and approximate, we're using an estimation. So if we write the equation of a tangent line at a point, then, so at x equals 2, then we can use the line approximation to estimate the value of f. So plugging in 2.01 into the tangent line is almost as good as plugging in 2.01 into the actual equation. Okay? Now you may ask, why would we want to do this? You know, can't we just, we have calculators, why can't we just plug 2.01 into the actual function? But I'm only using this example here to illustrate a concept. Later on, you will see some scenarios where we have a really, really, really complicated function, and rather than trying to evaluate numbers in that function, we can come up with the equation of a line and get an estimate that's almost just as good. All right, so that's the general idea here for local linear approximation. As always, keep working hard. Ask for clarification when you need it. Thank you for watching, and have a wonderful day.